Hello everyone, I'm Norman Wildberger, and today is our fourth and final lecture on Hamilton's discovery of quaternions. Today I want to explain how the theoretical framework that we developed in our last lecture can be applied in a very practical and relatively elementary way to help us concretely and explicitly work with rotations of three-dimensional space. So this should be of a special interest to engineers or computer programmers or video game creators who have to work with rotations of three-dimensional space. So our setup today relies on not using angles. We're going to adopt sort of rational approaches or rational analogs of angles which make the whole story much simpler. So this is a bit of a departure from the classical way of describing the relationship between quaternions and rotations. Okay, so let's introduce the main notion here is just the notion of the half turn. So I've talked already about turn, and the half turn is very closely related to that. And it's also very closely related to the important rational parameterization of the circle which underlies two-dimensional rotations. So here we have the standard plane with the unit circle, x squared plus y squared equals 1. And here on the circle is a point z with Cartesian coordinates x and y. And we know that that point can be expressed in terms of a rational parameterization in this form here. In terms of some rational number h, and this expression 1 minus h squared over 1 plus h squared is the x coordinate, and this one 2h over 1 plus h squared is the y coordinate. And the meaning of that number h is that it's the y coordinate of the point that you get by intersecting the line from z to minus 1 with the y-axis. And this number h is going to be called the half turn of the number z. Now I remind you that this line, we could also translate it so that it's actually going through the origin, in which case this number h can also be thought of as the y-coordinate of the point that you get where this line here meets this vertical line, the line where x equals 1. And when we think about it that way, we see that this number h is also the turn of this line. So from here to here, that turn of that is the ratio of the slope h over 1. So the half turn of this line is the same as the turn of this line. And this line here is actually a bisector of the vertex formed by these two lines here. And I want to mention also that there's a third kind of rational approach to describing the position of that line. That's the spread, which is important in rational trigonometry. It's usually called S, and that's, in terms of the coordinates x and y, is the number y squared. We're not going to use that, I'm just mentioning that out of interest. Okay, so these are all rational replacements of angle. We're going to be especially interested in the half turn. So it's a way of describing points on the unit circle, very classical going back to Euclid, and it's a replacement for angle. So just to make sure we're all on the same page here, let's roughly give some half turns for various positions. This position here, in practice, would be a half turn of roughly a half, because this position is roughly a half between 0 and 1. Down here, if we join that there, that might be half turn of 1/5, say. So maybe 1/5, 1/4, 1/3, 1/2, 3/4, 1. That's a half turn of 1. And then as the h moves up there, we might get to 1.5, to 2, to 3, to 4, to 10, and so on. Venturing in this direction, if we went down, say, to here, and that would be roughly minus a half, minus 3/4, minus 1, minus 2, minus 3, minus 4, minus 300, and so on. So it's a perhaps somewhat unfamiliar way of thinking about rotations or labeling rotations, but it turns out to be the best way of thinking if you want to understand rotations via quaternions. We want to measure rotations by half turns. All right, so please give this rational parameterization some more thought if you're not familiar with it. Very important. So we want to extend the idea of the half turn to more general vectors, not just unit vectors. So we have a general vector v in the plane, say with coordinates x and y. Then let's denote by r the length of that vector. So we're going to take the square root of x squared plus y squared. And we can work approximately, so we don't need to really fuss around with irrationalities here. As far as we're concerned, square root just means something that the calculator gives us, which is approximately a number whose square is x squared plus y squared. So that's the r quantity there. Now if we divide our vector by r, then we do get a unit vector. And we know that unit vector can be expressed rationally using some number h and the standard rational form for a point on the unit circle. So there's a point on the unit circle, the renormalized vector, and therefore we know that there must be a half-turn parameter associated to it called h. In terms of the original coordinates, this x-coordinate will be x over r, and the y-coordinate will be y over r. So giving a relationship between the half-turn h and the x and y coordinates and the length of the vector r. So now here is an important formula, which I call the half-turn formula, which allows you to compute this half-turn relatively simply from the vector v and its x and y coordinates. The formula is simply that the half-turn is equal to the radius r, the length, minus x divided by y. And I'm going to leave it to you as an exercise to prove this. You can just use exactly this relationship here, and hopefully you'll be able to see that this right-hand side can be evaluated to the quantity h. Let's illustrate it. So suppose we have some vector 3, 5. Then the radius or the length of that vector is square root of 3 squared plus 5 squared, which is square root of 34. And then the half-turn formula tells us that the half-turn of this vector will be root 34 minus 3 over 5. We subtract the x-coordinate, we divide by the y-coordinate. That's roughly 0.566. And so then we can refer to the pair r and h as the rotor coordinates for the vector. This is an alternative to polar coordinates, and it's a very powerful alternative to polar coordinates, which I'm going to describe somewhere else. This is a subject that I call vector trigonometry, and it has many interesting applications. So all what we really want for us today is to know that if you have a vector, then you can describe it in this alternate way. Instead of Cartesian coordinates, we can describe it in terms of its length r and this half-turn number h. And to calculate h from x and y and r, we just use this half-turn formula. So for example here, in this case here, the 0.566 means that if we go up here to the 0.566, which is roughly about here, and then go out like this, where we hit the unit circle, that's going to be the direction of the vector. So the vector is somewhere in that direction, and you have to go out length square root of 34 to actually get the position itself. Great. So now let's remind you of the basic setup of quaternions that we introduced in our last lecture. And if you're not very familiar with that, please make sure you've watched that last lecture. So the quaternions are a four-dimensional space. And we're going to picture that four-dimensional space in terms of a horizontal line, the t-axis, on which there's the number 1, and then a transversal plane, which is actually three-dimensional, which we're going to call V. And this three-dimensional space is a lot like the space in which we operate typically. It's the span of 3 perpendicular directions, L, J, and K. These are the unit vectors in 3 perpendicular directions, which are just like the X, Y, and Z directions normally. Here is a picture of the unit sphere in this three-dimensional transversal slice. And it's here that we want the rotations to act. If we have a general quaternion, it has the form t plus v, where t is some coordinate in this direction, and v is some vector lying in this three-dimensional transversal slice. So in terms of this representation of quaternions, here is the crucial formula for multiplication. So if we have 2 quaternions, Q1 and Q2, of the form T1 plus V1 and T2 plus V2, then the formula for multiplying them is this one here. It's T1 T2 minus V1 dot V2, so that's sort of the scalar part, obtained by multiplying the 2 scalar parts here and subtracting the dot product of the 2 vector parts. And then the vector part of the product is T1 times V2 plus T2 times V1 plus an additional term, which is the cross product of these 2 vectors, V1 cross V2. And it's this cross product term that makes this different from complex number multiplication. Otherwise, it looks very much like complex multiplication. Okay, so there's a very important special case. And the important special case is when we have 2 quaternions that are pure vectors. In other words, so that their t component is 0. So imagine T1 and T2 both being 0. What would we get? Well, in that case, we just get minus V1 dot V2 for the first component, and these 2 would be 0, and we would just get V1 cross V2 for the vector component. So that's the special case when we are multiplying 2 vectors inside the quaternions. In other words, 2 vectors which are lying in this transversal hyperplane. And now there's a special case of this formula, which is also very important, which is what happens when the 2 vectors v1 and v2 are themselves orthogonal or perpendicular. That translates to the dot product being 0. And in that case, the formula simplifies yet further to say that v1 times v2 is just v1 cross v2. So if we have 2 perpendicular vectors over here, their quaternion product is just exactly the same as their cross product in familiar 3-dimensional vector geometry. And another special case is this one here, that if we have a vector which is a unit vector, which is actually of length 1 or quadrants 1, so that its quadrants u, which is u dot u, is actually 1, then u squared will be equal to minus 1. Because in this formula, we'll get minus 1 for the dot product, and when we take the cross product of u with itself, we get 0. So we get the important formula that when we take a pure unit vector anywhere in this V space, then it will have the property that its square is minus 1. We already know that that's the case for the unit vectors L, J, and K. We know that L squared is minus 1 and J squared is minus 1 and K squared is minus 1. Now we learn that that property holds for any unit vector in this transversal plane. Okay, and here's a little exercise for you just to show that the dot product and the cross product can be rewritten using basically these laws to be expressed in terms of the quaternion multiplication. So strictly speaking, the dot product and the cross product are contained within the arithmetic of the quaternions. That was a major point made by the supporters of Hamilton in the kind of controversy between whether quaternions are the right way of describing physics, or whether the dot product cross product formulation of Gibbs was a better way. So the quaternion advocates said, well, the dot product and the cross product are just special kinds of configurations that we can cook up with the quaternion structure. There's nothing really new about them. Which is at some level true, but it's also true that the dot product and the cross product have a sort of independent existence. We don't really need the quaternions to define them. In fact, we're using them here to define the structure of quaternions. That's the way Gibbs would have replied. He would have said, well, we're just building up quaternions from the dot product and the cross product. Anyway, there's an intimate connection, but it's going to be very important for us, this formula here and this formula here, understanding the role of the unit quaternions especially. Understanding the role of these unit vectors, particularly, they all have this property a lot like the square root of minus 1, I usually in the complex number situation. So while the overall quaternion structure is a little bit complicated, we're working in this four-dimensional space, nevertheless it can be simplified by thinking about the multiplication in a particular way, and I want to show you that now. So this is going to be a good way of actually visualizing what actually happens when you multiply by a quaternion, geometrically. And it's really the key to understanding the connection between quaternions and rotations. So let's suppose we have a unit vector, u, in S2, just the kind that we've just been talking about. So here's our picture again, and here's our unit sphere inside this three-dimensional space V. And here's our unit vector u, which lies on this two-dimensional sphere. And we'll suppose that we have two other vectors, v and w, so that the triple u, v, and w form a right-handed system of perpendicular unit vectors. So they're just like the L, J, and K system that we started with, something like L, J, and K, that's a right-handed system. But now in some more general position, so u is the first one, and then v, and then w. Okay, so what do we know? Well, we know that u squared is equal to minus 1. And we also know from the formula on the previous page that when you have perpendicular vectors, then their product is just the same as their cross product. Okay, so that means that when we multiply u times v in the quaternion sense, it's exactly the same as the cross product of u and v in the three-dimensional cross product sense. So there's u and there's v, then the cross product of u and v is by definition w. So u times v is w, and u times w is minus v. So that's how u acting on the left acts. It sends v to w, and it sends w to minus v. On the other hand, v times u is the cross product of v and u, which is minus w. It's negative this one. And w times u is negative this one, so it's just v. And I want to visualize that in the following way. We're going to think about two-dimensional planes. So inside this four-dimensional space, we're going to think about two planes, which are actually two-dimensional. And the first plane is the plane spanned by 1 and u. So here I'm showing you that plane. It's the span of 1 and u. So we're going to forget about the other vectors. Just there's the vector 1, there's the vector u, and anything here is a linear combination of 1 and u. So it's kind of a slice in this direction of this four-dimensional picture. And the other plane that we're going to think about is the perpendicular to this plane, the orthogonal complement. All the vectors which are orthogonal to these ones. In other words, the span of v and w. There's a span of v and w, so there's v and there's w. So we're basically taking this sort of equatorial plane here in v and taking it out and putting it there so we can look at it. So there's v and there's w, minus v and minus w, and everything in this plane is a linear combination of v and w. Okay, there's a very good reason for thinking about it this way, because now when we want to understand the multiplication by u, it turns out we can look at these two planes independently. Okay, why is that? So let's look at multiplication by u in this plane. If we multiply, well, it depends on whether we mean multiply on the left or multiply on the right. If we take the vector 1 and we multiply on the left by u, we get u, which is the same thing that we get when we multiply on the right by u. So that's fine. And if we multiply u either on the left or the right, we know we're getting minus 1. So the action or the effect of multiplying by u either on the left or on the right in this two-dimensional plane is to move or rotate by a quarter turn. 1 goes to u goes to minus 1 goes to minus u, and minus u goes to 1. It's a quarter turn. It's exactly the same thing that we get when we look in the complex plane multiplying by I. And over here, we're going to look at the same story, but now in this transversal plane. What does multiplying by u do to the space v and w span? Well, these formulas tell us. If we left multiply by u, then v is sent to w. And w is sent to minus v. W sent to minus v. So in fact, left multiplying by u is also a quarter turn in the VW plane. What about right multiplication by u? Well, when we multiply v on the right by u, we get minus w. We go this one here. And when we multiply w on the right by u, we get v. So the effect of multiplying on the right by u is a quarter turn in the negative direction. All right, so let me summarize what I've just said. So we have these two different planes. When we multiply by u on the left or on the right, in this plane, both of them are quarter turns. However, over here, when we multiply by u on the left, we have a quarter turn, but on the right, by a negative quarter turn. The actions are subtly different. Here it doesn't matter what direction or what order we multiply because the situation is commutative in this little two-dimensional plane. It's just like the complex numbers. But here the action of u by multiplying on the left and on the right is different. It's also useful to think about the conjugate of u, which in this case is just minus u. So if I multiply on the left by the conjugate u bar, which is minus u, in that case, the action is to rotate by a minus quarter turn. which is the same as multiplying on the right by u bar. And over here, the results are also opposite to what they were before. So in this case, if we're multiplying by u bar, now the left multiplication by u bar is a quarter turn negatively, while the right multiplication by u bar is a quarter turn positively. All right, so this is the key to understanding multiplication by quaternions, is to realize that if we have a unit vector, then its action on the two-dimensional plane spanned by one end itself is one thing, and it's relatively easy to understand. And its action on that transversal orthogonal complement is also relatively easy to understand. And the two actions of multiplying by u on the left or the right, they both amount to 1/4 positive turn on this two-dimensional space, but they're different over here. Left multiplication is quarter turn, right multiplication is a negative quarter turn. A subtle but important crucial difference between the way u acts by multiplying on this two-dimensional space and how it acts on this two-dimensional space. And all of those statements can be checked. They're just immediate consequences of the formula that the product of perpendicular vectors is the cross product of those two vectors. We're just recording these very elementary cross products when we make these diagrams. Nevertheless, they're the key to understanding the action of quaternions on the space itself and by rotations. So now let's take what we've just done and extend it to understanding multiplication by a general quaternion. So our general quaternion that we're going to choose is, say, z, which has a scalar part, t, and a vector part, which we'll write as r times u, where u is a unit vector. So the story is, here's our general quaternion somewhere in this four-dimensional space. It has a t component, or the scalar component, t, and it has a vector component. And we want to write that vector component as r times a unit vector, where u is then a vector just like the one we've been talking about, lying on the 2 sphere over here of unit vectors. And r is just some multiple of that vector that we're going to take. And we're going to suppose that this unit vector that we've chosen comes along with another pair of vectors, v and w, so that just like in the last slide, we have a right-handed triple of unit vectors in our v here. U, v, and then w. Okay, so what I want to do now is I want to show you what multiplication by z does. And I want to do that in two separate planes. The first plane is the plane spanned by 1 and u. So there's 1 and there's u. There's the unit circle in that plane. And the other plane is the plane spanned by v and w. V and w. So these are exactly the same two planes that we were talking about last time. Now we know what multiplication by u does in this plane. It's just a quarter turn, just like multiplication by I in complex numbers. So what does z equals t plus ru do to this plane? Well, first of all, t plus ru is actually an element in this plane. There's t and there's ru, so there's our quaternion that we're talking about. It's actually sitting in this two-dimensional plane. And the arithmetic in this two-dimensional plane is exactly the same as the arithmetic for complex numbers, because the u acts just like I does. Its square is -1. And so that means that when we multiply by z, the effect is exactly the same as multiplying by this associated complex number would be if this was a picture of complex numbers. In other words, if here's 1 and here is z, then if we multiplied by this complex numbers, if this was a picture of the complex numbers, we know we would get a combination of rotation and dilation. It would be a rotation dilation, which rotates by exactly this amount and dilates by enough so that this gets stretched to that. Just a combination of the identity, which doesn't do anything, and this u, which is a quarter turn. So both left and right multiplication by z do exactly the same thing. They rotate by this amount, and they scale so that this 1 gets blown up to that point there. And that's happening to the whole space. We're getting a rotation dilation just like we do when we multiply by a complex number. In fact, exactly the complex number t, comma r. All right, now more challenging, what happens over here in the VW plane? Well, we know what multiplying by 1 does. It doesn't change anything. And we've just learned what multiplying by u does. It rotates by a quarter turn. So the action of 1 and the action of u are in this plane exactly the same as they are over here. When we multiply on the left by t plus ru then, we're going to get exactly the same kind of story that we're getting over here. Namely, it's going to be a combination of rotation and dilation. So that this v is going to get sent to sort of the corresponding position up here. That will be z times v, which will be the combination tv plus rw. The same combination of v and w that we had over here, the combination of 1 and u. However, multiplying by z on the right is different, because multiplying by z on the right in this space is a quarter turn in the negative direction. And that means when we're multiplying on the right by this z, we're getting also a rotation dilation by the same amount, but rotation in the opposite direction, so that this point here would get sent not up to here, but to the corresponding reflected point down there. All right, so now we can put that together to form this sort of combined rotation construction, which I introduced last time. This is almost the same as what I wrote down, but I've changed my notation just a little bit. So last time I had a z bar qz. I've decided to change that. Makes it a little bit simpler with the way I've set things up. Z q z bar. It's a little bit less standard, I think, but more convenient for us. So given this z, we're defining this operation on a general quaternion. Z times q times z bar divided by q of z. All right, now we can see why I think the effect of this is going to be a rotation of just the v-plane. Let me try to explain that to you now. Let's look at the effect of this in these two planes separately. Over here, if I multiply by z, that's a rotation dilation in this direction. And when I multiply by z bar on the right, I'm getting a multiplication dilation in the opposite direction. So the cumulative effect of multiplying by z on the left followed by multiplying by z bar on the right is that the directions cancel out, and we just end up scaling by q of z. So that when we divide by q of z, the effect is to leave everything here completely unchanged. We can see that directly algebraically. If you just plug 1 in here, you see that you still get 1. And if you plug in u, you can compute that you still get u. So this thing here does absolutely nothing to this two-dimensional plane. It leaves everything fixed. The interesting thing is, what does it do to this plane? All right, so now we're left multiplying by z, and then right multiplying by z bar. All right, so left multiplying by z was a rotation dilation in this direction, but right multiplying by z bar was exactly the same thing. They were not in opposite directions now. Over here, left multiplying by z and right multiplying by z bar are exactly the same. So when we do this one and this followed by this one, we're basically doing twice the same thing. We're dilating, rotating by z, and then we're doing the same rotation in the same direction a second time. So the effect is that, say, this vector v, first it gets sent to zv, a rotation dilation by that amount. And then when we multiply by z bar, we rotate and dilate again by the same amount and dilate it up as well. And then after we normalize by q of z, we are just normalizing back down to be on the unit circle, showing us that what we're getting is a rotation by essentially twice this configuration. The turn here is h, then the turn here is also h, and the total half turn of this is then h. Right? This is exactly the kind of situation that's described by a half turn. If the turn here is h, the turn here is also h, then the half turn of the composite is just h. And what is the turn of h here? The turn is the turn associated with zv, or the turn associated with this thing here. It's r over t. So r over t is the half turn of the rotation that we're getting in this VW plane. So to summarize, what happens when we perform this particular combination is that it leaves this direction unchanged. It leaves the u direction unchanged, but it rotates in this three-dimensional space along the axis of u. And how much does it rotate? It rotates by a half turn, and the half turn is exactly r over t, the ratio of the y component here to the x component, t. So the r multiple, the t multiple, the ratio r over t is the half turn. That's describing how much rotation we're getting in this transversal plane to u. So this explains, first of all, why this is a rotation. It explains why it's a rotation in the direction u, in the direction of the vector part of the quaternion we're talking about. And it explains how to get, or how to describe, the amount of rotation. The amount of rotation is given by the half turn r over t. So that r divided by that t is the half turn of the rotation that we're getting in this transversal plane to u. That's how quaternions connect to rotations. And with half turns, the connection is very simple because it's just that r divided by that t. With angles, it's more complicated to deal with. It's more complicated. This is really a nicer way of thinking about how quaternions act. Okay, so let me summarize what we've just done. That if we have a quaternion Q with a expression t plus v, so scalar part t, vector part v, and here's our rotation mapping. So phi sub q takes a general quaternion q prime to the combination q times q prime times q bar, all divided by the quadrants of q. Then that's a rotation of v. And it's a rotation actually about the vector v, with a half turn given by h equals the size of v over t. And also there's this formula for the composition of two such rotations. If we rotate by the transformation phi sub q1 followed by the rotation phi sub q2, then that's what we get when we first multiply by q1 on the left and q1 bar on the right, and then multiply by q2 on the left and q2 bar on the right. Well, that has the cumulative effect of being the rotation generated by q1 times q2. So the multiplicative structure of the quaternions is directly then responsible for the composition of rotations because of the pleasant aspect of this formula. Okay, so let's have a look at an example. Let's suppose that Q is 1 plus R times L. And I should say that R is going to be a positive multiple here. So we're thinking of this actually, this vector part is really in the direction of L, not in terms of in the direction of minus L. The direction matters. Okay, so then we know that phi sub q is going to be a rotation about L, which is the x-axis of V. Remember, L was one of our three standard unit vectors, L, J, and K. And the half turn of this rotation associated with this is given by this ratio R over 1, which is R. That's going to be the half turn. Okay, so what's it look like? So here, for example, is the two-dimensional plane spanned by 1 and L. We're looking at a quaternion that's somewhere on this line of the form 1 plus RL, actually up in this direction somewhere. And if we take this point here and we sort of square it, we get up to here, and if we normalize, we get this point here, so that this turn and this turn are equal. And that's the amount of rotation that's responsible, or that's being given by this particular phi sub q. But the rotation's not happening in this two-dimensional plane, it's actually happening in the transversal plane spanned by J and K. So here's our three-dimensional picture of V, in which we have the x-axis, say here, y-axis here, and z-axis here. Unit vectors L, J, and K. Then the phi sub q here is going to generate a rotation about the x-axis, coming out this way. It's going to be a rotation like this, sending the J and the K to some combinations of them along the unit circle there. And the amount of rotation here is exactly the same as the amount of rotation in this diagram over here. In other words, the rotation is such that this is a half turn, which is exactly that of R. There's a turn of R, so this whole thing has half turn R. So it'll be that amount there. J will be sent to that, K will be sent to that. That whole perpendicular plane to L will be rotated. That's what Q equals 1 plus RL does. So let's have a look at what the workings of that example look like in terms of these 2x2 matrices that we like to associate with quaternions. That allows us to do the calculations in a 2x2 matrix framework, which is much more convenient than a 3x3 framework that we would get from linear algebra if we did things in the standard way. So with the particular quaternion that we're looking at, it was 1 plus R times L. So it's associated to the 2x2 matrix 1 plus IR, 0, 0, and the complex conjugate 1 minus IR. Remember that the coefficients of 1, L, J, and K get written here as complex numbers, and here there's a complex conjugate, and here there's a minus complex conjugate. If we take a typical vector V in our three-dimensional space with coordinates x, y, and z, then its associated matrix is this one here. And then we can do this quaternion multiplication with complex number matrices if we want to. We don't have to, but it's one way of doing it. So m sub q, m sub v, that 2 by 2 matrix, m sub q bar, complex conjugate, dividing by the quadrants of q will be 1 plus r squared we have to divide by. Doing this matrix multiplication is pretty easy because when we multiply by that diagonal matrix, well, we're multiplying the first row here by 1 plus IR, second row by this thing, and then here we're multiplying the first column by 1 minus IR, and then the second column by 1 plus IR. So the cumulative effect is to multiply the first entry here by 1 plus R squared, actually here and here, and to multiply this entry by 1 plus IR squared, and this one by 1 minus IR squared. Okay, and when we divide by 1 plus R squared, we get this as the formula, that this 3 vector ends up getting moved to this one here. The x coordinates haven't changed, but the y and the z coordinates have been changed by, in terms of complex numbers, they're just being multiplied by this quantity here, 1 plus IR squared over 1 plus R squared. And what does that do? Well, we've seen this kind of thing before in our discussion of complex numbers. This is in the complex number plane. If we're multiplying by 1 plus IR all squared, there it is, 1 plus IR, there's its square. We divide by its quadrants. We end up rotating from here to here, essentially reflection in this line. This shows that, yes, indeed, as claimed, this operation does indeed take the YZ coordinates and rotate them by exactly a half turn of R. Because in the complex number coordinates, that's exactly what's happening to those two numbers y and z. So in my final example, let's show how this can be used to actually help us compose rotations. So we're going to consider the following problem. What is rotation about v1, which is the vector 1, 1, 2, by a half turn of 0.8, followed by rotation about the vector 3, minus 1, 2, by an angle of 110 degrees. So we're mixing half turns and angles here just to give us some practice in going back and forth between them. All right, so the solution is that we're going to compute quaternions for each rotation, and then we're going to multiply those quaternions to get the composite quaternion. All right, so let's look at the first rotation, which is going to be given by a quaternion of the form T1 plus V1. What do we know about this quaternion? Well, we know that the rotation had better be about the vector 1, 1, 2. So the vector part can be chosen to be 1, 1, 2. But how are we going to choose this T1? Well, we have to make sure that the half turn associated to this quaternion, which we know is the length of V1 divided by T1, that better be 0.8. Well, the length of V1 is the square root of 1 plus 1 plus 4. So the square root of 6 over T1 had better be 0.8. And so we can solve for T1 approximately something pretty close to 3, say 3.06. So that's a specific quaternion. The scalar part is this. The vector part is this. We know that that's going to give us a rotation about this axis with a half turn of 0.8. Okay, let's have a look at the second rotation. That's a rotation about 3 minus 1, 2. Okay, but the angle is 110 degrees. Well, we don't want to use angles because our whole setup is geared towards half turns. So we have to convert the angle to a half turn to make the algebra work out nicely. So how do we do that? Well, here's a picture of the unit circle. There's an angle of about 110 degrees. Let me remind you geometrically what it means to find the associated half turn. So we look at this point on the unit circle. We join minus 1 to it. We get a line that meets the y-axis in some point with a coordinate h, or h2. That's the half turn associated with this rotation. So we need to find that coordinate of that point. Okay, we can do it diagrammatically. It looks like it's going to be something more than 1, something between 1 and 2. We can also do, because we know that cosine of 110, this point here, the x-coordinate, is going to be 1 minus h2 squared over 1 plus h2 squared. Or we also know that the sine of this thing, sine of 110 degrees, is going to be 2h2 over 1 plus h2 squared. So you can use either one of these to solve for h2. All right, so we do that, and we find that h2 is approximately 1.428. So somewhere in this range up here. So that's the half turn associated to this thing here. And then what's the scalar part of it? Well, the half turn has to be the size of the vector divided by that scalar part. The vector that we're choosing is 3 minus 1, 2, so its length is square root of 9 plus 1 plus 4, which is square root of 14, over t2. That's got to be the half turn. And that tells us the scalar part t2 is going to be 0.7003. So the quaternion associated to this rotation is going to be the scalar part plus that vector part. Okay, so the two quaternions that we found, first one was t1 plus v1, so there's the t1 and there's the v components. And the second one, t2 plus v2, there was the t2 we found and there were the vector components. There's the formula that tells us that to compute the composition, we're going to perform that rotation followed by that rotation, we need to compute the product of the quaternions, with the q2 first and the q1. Okay, so here is the formula in terms of scalar and vector parts. It's going to be t1 t2 minus v1 dot v2, and then t1 v2 plus t2 v1 plus v2 cross v1. And it's v2 first because the q2 is on the left here and the q1 is on the right. And the order does matter here. Order doesn't matter here. All right, so then you have to make this multiplication. So you can compute the dot product between these two, not too hard. You can compute the cross product between those two and add them to these ones, and you will get this quaternion. Minus 3.858, 5.88, minus 6.36, 11.52. And that's the quaternion that represents the composite rotation. Now the beauty of this approach is that if we multiply the quaternion by a scalar, the rotation associated doesn't change. It's only really the line going through Q that determines the rotation. So we can, if we feel like it, scale this down. Now in classical treatments, it's generally thought that we should scale it down so we get a unit quaternion. We could do this, but it's not really necessary to do that because that involves finding another square root. Another way of proceeding, which is quite pleasant, is to renormalize so that this first coefficient is 1. We've seen the advantage of that in many situations, and I'm going to do that here too. So I'm just going to divide by minus 3.858 to rescale this quaternion, so now that its first entry happens to be 1. Give some kind of canonical form to the quaternion. Okay, the rotation associated to this one and to this one are the same. And now we can read off, well, what is this rotation? It's a rotation about this vector with a half turn of, well, we have to take the length of this vector and we have to divide by 1. You can see the advantage in having a 1 here. It means that the half turn is just the length of this vector, which is 3.74. What is that as an angle? So here's the picture. Okay, unit circle, 1, 2, 3, 4. So H is 3.74 up there somewhere. Take that line there, you see where it meets. It turns out to be somewhere close to 150 degrees. And you could compute an angle if you wanted to. Once you know h, you can compute the angle theta if you feel like it. You don't need to. Convert it, say, something to close to 150 degrees. So we found the composite of these two rotations. Here is the new axis, and there's the new half turn. And I want to try to illustrate what's going on here if I can. So here is a picture of here's a sphere, okay, and I've got some kind of coordinates here. So you can think of this as being the x-coordinate coming at you. There's a north pole up here, there's a south pole down here, sort of an east pole here, and a west pole on that side there. And on the opposite side to the point that we've got sort of the opposite, the antipodal fellow in green on that side, just to orient us where we are. All right, so let's start here. And the three rotations were, well, the first one was a rotation about the vector 1, 1, 2 by a half turn of 0.8. So 1 from the center coming out there, in the x direction, 1 in the y direction, and then 2 up. That would be a vector which is emanating somewhere there, and its axis is roughly this axis right here. You can see that? Okay, and I need to rotate by about a half turn of about 0.8, which is close to 90 degrees. So it's roughly 90-degree rotation, something like that. That's the first rotation. Starting here and rotating like this. Okay, our second rotation is rotation about the vector 3, minus 1, 2. Where is that? 3 x direction coming out here, minus 1 in the y direction, up 2. Okay, so it's a vector like this. It's a vector roughly with an axis like this. And we're supposed to rotate by an angle of 110 degrees. So that would be maybe about 110 like this. So that's our second rotation. Okay, now we're supposed to do one after the other. So let's do the composite. Let's do our first rotation, which was around this axis, by, we said, well, somewhat little bit less than 90 degrees. So we'll better start in the right position. There's the axis, and now I'm going to rotate by hopefully a little bit less than 90 degrees. So something like that. Okay, now without moving the sphere, I have to find that second axis. You remember it was something like this. This is rather inaccurate, but okay. There's the second axis. It was in that direction. And we were going to rotate by 110 degrees. So let me do that again. 110 degrees. Okay, so we end up with this position here. That's the composite. So where is our original guy? Our original guy is back here, okay? Sort of the opposite end there. All right, so now let's have a look at the final composite. Should be a rotation around this vector here. So minus 1.52, that would be in that direction, the x direction, 1.65 in the y direction, and minus 3 in the z direction. And that's an axis that's roughly like this. And we're supposed to make an angle or rotation of about a half turn of 3.74, which is roughly 150 degrees. And that's with respect to this direction of my right hand. So 150 degrees, almost 180, but not quite. All right, so let's see what that would amount to. So there's our axis, and roughly we're going to go 150, about like that. And I hope you can see that that's kind of the same, pretty close to the composite of the two rotations that we considered earlier. So that's how Hamilton's theory of quaternions actually gets used in practice. At least it's my presentation of it. I'd be interested to know how widespread the use of essentially half turns is in the industry. For example, people who work in movie studios, Pixar or Walt Disney's or whatever, lots of 3D animation, whether they commonly use this approach of circumventing angles. I think it has much to recommend it. Rational approach to geometry. So Hamilton's very, very important discovery here has a lot of other ramifications that we are going to see later on in this series. We're going to see us talking about quaternions again when we talk about the problem of how to represent motions of three-dimensional space, not just rotations, but also more general movements involving translation as well. And we're also going to see quaternions when we have a look at relativistic geometry and Einstein's problem of how to understand rotations of a relativistic forest space. In our next video, we're going to look at some famous problems from Japan, so-called Japanese temple problems, which were basically geometrical puzzles that were often posed to the general public by people who posted them on the doors of temples. And some of them are very interesting and intricate. So we'll have a look at them next time in this famous math problem series. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.